It's important to realize that a unique feature of gases is that their particles are in rapid random motion. So the molecules or atoms that make up a gas are moving around very, very quickly in a random fashion. And as a result, they do a couple of interesting things. And two interesting things that they do is that they diffuse, that means they spread out through space, and they effuse, which means that if we have a container containing a gas and we put a hole in it, it will leak out of that hole. So, consider a box full of a gas, and it's got particles in it that are moving around rapidly in all directions. They're just kind of randomly moving around. And now what we're going to do is we put a hole in our box. And if we think about what will happen is, these particles, they bounce off the container walls, and every now and then one of them is going to be on a trajectory that sends it through the hole, and the gas will leak out of the hole in the box. So that's not surprising, and if we wait long enough, all of the gas will leak out the hole. So the process through which a gas leaks out of a hole in its container is called effusion. So it's interesting to think what property of the gas will affect the rate at which it leaks. So if you was to close your eyes and just sort of like stumble around at walking pace, eventually you would collide with the door of your room. But if you was to close your eyes and run, it would take you a lot less time in order to collide with the door of your room. So what we can see is that the property of the gas that's going to affect the rate at which it leaks is the speed of movement of the particles. And how is that? What is that going to be related to? Well, that's going to be related to the temperature, isn't it? All right. So as the temperature increases, the speed of our particles increases, and our gas will leak out of the hole in its container quicker. So if we're just going to kind of think about a gas sample that's at constant temperature, we're just going to talk only about the speed. So if we want the speed of our gas sample to be fixed, then we need to be at a constant temperature. So this is what we can say. The faster the gas particles are moving, the quicker the rate of effusion. Now, it turns out for a gas at a given temperature, at fixed T, that the speed of the gas particles, which we're going to indicate using this symbol, that's the root mean squared speed, is inversely related to the square root of the molar mass. So what we're really saying is that as the molar mass of our gas particles goes down at a given temperature, the speed goes up. So if you're a light and skinny gas molecule, at a given temperature, you're going to be whizzing around very, very quickly. And if you're a big, muscly, heavy gas molecule, at a given temperature, you're going to be going a lot slower. So what we would expect is that at a fixed temperature, light molecules are going to leak out of a hole quicker than heavier molecules. And you can imagine this being used to separate gases with different molar masses. And sure enough, we do this. In fact, we do this when we purify the different isotopes of uranium in the manufacture of enriched uranium. So this whole thing is summarized by Graham's law of effusion, which states that if the temperature is fixed, the rate at which gas X diffuses out of a hole divided by the rate at which gas Y diffuses out of a hole is equal to the square root of the molar mass of Y over the molar mass of X. And the important thing here is to see that your X's and Y's are on different sides of the fraction symbol. So that's what's going on. So if you know that X is diffusing at 4 times the rate of Y, then, you know, we can kind of start doing some calc, and we know the molar masses of X and we know the molar masses of Y. We can start doing some interesting math and figuring out what's going on here. So what are you going to have? Generally, you're going to have 3 of these variables that go into this expression, and you will be solving for the 4th one. Okay, so let's give an example calculation. It says hydrogen effuses 4 times faster than gas X. Now, hydrogen is always going to be the gas that effuses the quickest of all gases because it has the smallest molar mass. And then the next one will be helium. And you might have recognized this, that if you've ever purchased the helium balloon, that after a while it goes flat. And the reason is that the helium will effuse out of the pores in the latex or the mylar in a balloon. So this says helium effuses 4 times faster than gas X. What is the molar mass of gas X? So I know the molar mass of hydrogen. So it's 2.02 grams per mole. And I know that the ratio of the rate of effusion over the rate of effusion of hydrogen over the rate of effusion of gas X is 4. So what I can do here is say that 4 is equal to the square root of the molar mass of hydrogen over the molar mass of X. And so now I just can solve. I have to square both sides, so I would end up with 16 equals the molar mass of X over the molar mass of hydrogen, and then reorganize and get the molar mass of X. And it ended up being 32.3 grams per mole, which is approximately the molar mass of oxygen. So that's interesting. If you were to fill a balloon with hydrogen, the gas would leak out 4 times quicker than if you used to fill the same balloon with O2, with oxygen gas. So that's interesting, isn't it? All right, so you get the idea. You'll have 3 of your variables, and you'll be reorganizing and solving for the 5th. This one was kind of like a little weird in that they didn't give you the absolute rates of the hydrogen and gas X effusion rates. They gave you the ratio of the 2. So it actually kind of made it a little easier, didn't it? It actually said that it was 4, that the hydrogen effuses 4 times faster than that of gas X, right? Because the rate of effusion of hydrogen is 4 times the rate of X. Okay. So there's a related process to effusion called diffusion, and diffusion is all about how one gas disperses through another. So when you breathe out carbon dioxide, that carbon dioxide doesn't just kind of like linger in front of your face. It's going to disperse out throughout the whole atmosphere. And so this rate of dispersion, or we call diffusion, is also given by Graham's law. Now, if you're anything like me, you'll constantly muddle up the terms effusion and diffusion, and that's okay in everyday speech, but you do obviously want to be careful when you're giving answers to questions in your tests and other quizzes and exams. And you can just remember that effusion begins with an E, and it means to exit, which also begins with an E, and diffusion starts with a D, which means to disperse, and disperse also starts with a D. So these problems, whether they're concerning effusion or diffusion, are all governed by Graham's law, and you have to remember that even if it's not mentioned, this applies at fixed temperature. Okay, so that concludes the video for this section. I hope it was helpful.